Hello and welcome. This is module 5. As you see, we keep dropping down to different layers. So now we're at layer 1. So this is where your cable in, your fiber, where your medium to transmit your data goes. So we'll go over the basics, your frequency, bandwidth, throughput, multiplex, and different things. Describe the physical, for physical characteristic of a cable, twin ax, twisted pair, fiber optics. Uh, Wireless is not here, but wireless, remember, uses radio frequencies to as a layer 1. So the layer 1 on wireless, is still over the air wireless, radio communication, but is not covered here. It will be covered later on another module. We'll compare some of this and then talk about more of some of the troubleshooting that you can do on the cabling. So we'll cover a way to measure the efficiency of the network, how fast or how efficient you can send a communication through it without having any errors on the transmission, and what actually creates those errors on that medium that you're using. All right, so the data on a wire or any medium can have 3 measurements: frequency, bandwidth, and throughput. Frequency, remember that everything is ones and zeros, right? So every when you go every 1 and 0, every 2 is a cycle. So you go on or you're off, or you go on or off. So the frequency is the measurement of how many times that signal can change states, or how fast it can change states. So how long it stays on and how long it stays off, it depends on the frequency. The higher the frequency, the shorter that time that it stays on or off. So something that has a very low frequency, it just goes on and off and on and off and on and off. Something that has a higher frequency, it goes on off on off on off on off on off. So it's a higher cycle, and it's measured how many times it changes per second. So you can typically it's measured into megahertz or gigahertz. The electricity that we get on the wall is usually 60 hertz, so it cycles 60 times per second. Bandwidth is the amount of data that you can transmit on a given time, right? And then throughput is how much you can actually do on that time. So bandwidth, I compare that with a pipe. So you have a small pipe, let's say a 1-inch pipe. There's so much water you can get through there, right? Your throughput is kind of slow. If you get a 3-inch pipe, which is a bigger pipe, more bandwidth, then you get more throughput because there's more water going through. Now, the throughput also depends on your water pressure, right? If we're talking about water, so you can have a 3-inch pipe, but if you have a very low throughput, then you have 3 inches, but you have very low amounts of gallons per second that can get through. If you have very good strong pressure, you can get a lot of gallons of water over a period of time, over a second. So that's the same thing. So the bandwidth is the capacity that it can have, and basically throughput, how much you can go push through it. Now, errors that you can get or flaws on your transmission are measured in dBs. dBs is we measure in dBs the noise that you can get on a signal. Now, when you get noise or the greater of the signal, you get less of a signal. If your signal is completely unchanged, it's called 0 dBs. When you get 0 dBs, it's no gains, no losses. If you're talking about an amplifier, you can amplify 1 dB, 2 dBs, 3 dBs, or something like that. It's a positive, right? When you're talking about degrading or distorting the signal, then you get a minus measurement on dBs. You get a -3, -4, -50. It depends on what your measuring is, but negative dBs, it will show you degrading. Positive dBs show you increasing on the signal, which in networking you don't get that unless you are amplifying the signal. Then the other noise is the EMI that we talked about it. That when you talk about close to motors, power lines, televisions, in fluorescent lights is one of the worst for networking. And also, if you have a kitchen that is a microwave oven, that actually generates a lot of interference on the cables. So you have to stay away from that. On a building where you get motors, well, the air conditioner might have blowers inside. inside the plenum. Most likely there's more motors there to push more air into the air ducts. Elevators or anything like that, any motor is actually installed in the ceiling, you'll get that. Sometimes air conditioning is installed above the plenum, so you might have some AC units in there. You have to stay away from those. Um, Another noise that you can get is the crosstalk. Crosstalk is there are different ways to measure it. The alien crosstalk is between two cables. When they are too close to each other, one magnetic field interferes with the other magnetic field. On any wire, when you have any current going through it, there's always a magnetic field around it. Power lines will have that. Any power connections they have in the ceiling, and even low power, 48 volts or 24 volts, will have that magnetic field. So you have to make sure that things are away from those cables. And then there's also um, the crosstalk that can happen near end crosstalk, which is close to your source, and the far end crosstalk, which is it happens at the on the far end on the other end. So if it's close to your equipment, it's called near end. It's not at the end; it's actually near to you. And then the far end is far on the other end. More flaws, attenuation is one of them. Attenuation happens when the signal travels through, through especially a wire, even through fiber can happen that. There's a medium you go through there in a copper wires as it goes through. That's you get attenuation, so you lose some signal. And then it gets to a point you might lose the signal completely. That's why when you do Ethernet, you cannot get more than 100 meters. If you go past 100 meters, attenuation is so much that you lose the signal. To overcome that, you can get a repeater. The repeater will generate the signal, which works pretty well. Since the signal is digital, ones and zeros, so it could be very jagged on the signal, the way you loosen it. But since the timing, that frequency is always the same, the repeater can duplicate that frequency and reconstruct the signal specifically to the ones and zeros exactly, and make it a nice square signal without the errors. Latency is a delay. So every time you see latency, I mean the word late is in there. That means that latency is something that it gets delayed. So it takes a little bit of time to get there. Of course, when electrons travel through a wire, there is some latency across because they need to travel. Even though they travel at the speed of light, there's still some microseconds delay from one place to the other. Even speed of light is very fast, but it still has a limitation, right? It's not instant. So you still get some latency even on fiber. And that depends, of course, on the length of the cable. The longer it is, the more interference you have, the latency you have. The more bends you have on a fiber, the light has to traverse the bend, and that will delay the signal. Okay. Then there's the RTT, the round trip time. That's kind of like the ping when you send it. When you send a signal and it goes from the sender to the receiver and back to you. That's what's called the round trip time. So you can measure that and see how long is the delay on a signal. So how much latency you have, right? Now, if you have variation on the signal, that it is not like constant, and things get even out of order. That's what's called jitter. So jitter, you'll see that packet variation that would affect a lot of the voice. So if you get jitter, it will affect some of your voice communication. Now, the duplex is important to know. This is something that you set on your network card, and especially settings that you can have there, or sometimes the equipment is made to communicate in a specific duplex. So you can have full duplex, which is a both communication at the same time, meaning that the device can send and receive at the same time. That's called full duplex. Half duplex is when signal can travel only one way. So either you talk or you receive, but the equipment cannot talk and receive at the same time. When you do a phone conversation with someone, it's always half duplex, right? Because you talk, when you finish, the other person can call you back. I don't know if any of you remember the old Nextels or the walkie-talkies. On the walkie-talkies, you need to talk first. When you finish your conversation, what you're saying, your phrase, then you have to let go of the button and Lego the line so the other person can actually talk back. On a regular phone, you have full duplex where you can both can talk at the same time, even though you're not going to understand each other, but you can both talk at the same time. And then simplex is when it goes on one direction. It's just a one-way communication and nothing comes back. Simplex is used on usually alarm systems or sensors, things like that. The sensors would actually, I don't know, temperature sensor. It will read the temperature and it will send that signal back, to whoever needs to equipment that it is reading the signal, and it will send the signal, the information, but it's not expecting anything back or nothing is going to go back. It's kind of like the UDP. You send it once and you don't expect anything back. So you can configure that on your network card. Now, let me tell you something. Half duplex and full duplex can be configured on the Ethernet and fast Ethernet connections. Ethernet was the 10 megs. Fast Ethernet is 100 megs. When you go to 1 gig connection, copper, there is no such a thing as full duplex or half duplex. That happens only with the 10 meg and 100 meg connections, which is kind of like old, but still being used. Alarm systems and things like that. The manufacturers are going to put a 1 gig interface when the electronics can be a lot cheaper if you put a 10 meg or 100 meg interface. It's a lot slower, but what the information that they send across is so little that it doesn't matter. But you still have to support it on your network. And when you support 10, 100, then you have to be able to configure full duplex or half duplex. Even with 100 megs, you have to be careful with the full duplex because the full, sometimes you want to make sure that both ends are configured the same way so they're both talking full duplex, because you can have a duplex mismatch. When you get a duplex mismatch, you get a lot of error communication because one thinks he can do full duplex and the other one is doing only half duplex. So there's a lot of retransmissions that happen in there, and you will get an error that's called duplex mismatch. Now, if you go to the Windows Device Manager and configure your network card, you will see that under Advanced, there's one setting for speed and duplex. And you see there from the screen that you got 100 half duplex, 100 full duplex, 10 half duplex, and 10 megs full duplex. And the gig is only full duplex. There's no such a thing as a half duplex 1 gig connection. It is not. If they ask you that on an interview, or if someone tries to be smart and ask you, hey, did you set up that 1 gig connection full duplex or half duplex? That means that person don't know what they're talking about. Or you can just tell them, you're trying to be smart on me, because there's no such a thing as a half duplex on a 1 gig connection. Now, multiplexing, it's a way to transmit multiple signals at the same time over one medium. So you can carry multiple ways. There are different types of multiplexing for analog signals or for digital signals. It depends on kind of the multiplexing technology that you'll be using. But this is a way that you can multiplex everything into one communication and then have that spread out on the other end. So basically, you multiplex it or you mux it. That's the device that actually combine everything into one channel, and then you demultiplex it or demux it. When you demux it, then you separate that back into different signals. Imagine if you have a light transmission and you can have multiple colors, right? Multiple colors of light. You can compress that into one signal. You get it across the wire. When it gets to the other end, you demux it, and then you get all your different colors back on. So the green talks to green, the blue talks to blue, the orange talks to orange, and like that. The different colors, the different colors of light, and that works because if I'm sending with a blue sender and I'm expecting to receive a blue signal back, or expect to receive a blue signal, when I see green or yellow or blue, I'm not going to listen to any of those. I'm going to listen to only the one that have a filter on, which is blue, and just receive the blue signal. So when you multiplex it, there are multiple ways to do it. On copper lines, you do TDM, time division multiplexing. What it will do, it will do multiple time intervals, and then each communication takes, let's say, channel A, B, and C. So you will go with time for A, time for B, time for B, and then you repeat that. A statistical time division multiplexing is TDM that uses different slots, but the slots depend on priority and the need. So on this one, on a statistical multiplexing, you can prioritize voice or video, anything that is important, and it will go first. And then what is with less priority, it will take a different one. And then last is frequency division multiplexing, FDM. That one assigns different frequencies for each communication. It's more like subchannels. This one is very similar to your cable TV. Cable TV uses different signals for different channels. So channel 2 uses one frequency, and channel 10 and channel, I don't know, 33 use a different frequency. So the receiver is actually listening only on that one specific frequency. So all the other ones can be there, but for that receiver, everything else is noise. Because all I want to receive, let's say, is channel 4. So channel 4 is being encoded on a specific frequency, and when I receive it, I know that I need to receive it on that specific frequency. Everything else is noise. Then I can have another one for channel 10, so receive on that specific channel 10 frequency, but everything else is noise to me because I'm not going to listen to any of those. I listen only to the specific frequency that I have. But this way, I can send multiple frequencies over one wire, and then on the other end, when I receive it, I also select which one. It's kind of like you tune in your TV to a specific channel. So now your filters is, oh, listen only to the frequency for channel 4, or listen only to the frequency on channel 10. Now, if you go into fiber optics, the previous one was for a wire communication. If you go on fiber optics, then you have wave division multiplexing. Wave division is on a different wavelength. The wavelength is the color or the light, right? So it depends on which wavelength you have. It's the same thing as the different frequency. Wavelength is a color frequency. So it will multiplex it and demultiplex it based on that wavelength. Like I said, wavelength is a frequency of the color. And then you have the dense wavelength division multiplexing, which increases the number of channels. Basically the same thing, but you got more different colors that you can combine and then mux it and then demux it on the other end. And the coarse wavelength division multiplexing is a lower cost, but also spacing the frequency of the bands a little bit wide apart, so there's no error or interference between one and the other. When they're too close to each other, you might do a crosstalk between the two frequencies. So you separate the frequencies a little bit more space in between. So the frequencies that are not so close to each other, what you can do is pick, let's say, 10 frequencies and one every other. You have one in use and one not in use, one in use and one not in use. So by leaving that space in the middle, you avoid that crosstalk, and it's a little better transmission, but it's a low cost, and then you waste also on the transmission, but it's used to. Now, coaxial cable and twin ax cables are used. The old coax cable in the 1980s for media services for broadband, where you have your cable, your internet, and even phone on one cable. The coaxial cable is just one central core with an insulator and then a shield around it. You probably have seen that cable sometimes. They use, the RJ6 or RJ59, depending on what type of cable you're using. And you either use the F connector or BNC connectors. I like that in this book, on this edition. Now they're combining the coaxial cable with the twin axial, which is kind of like it's the same thing, but on the twin axial you have two cables inside rather than one. But some of the high speed communications now for equipment to equipment are using twin ax cables. So that will provide a better communication between the two equipments, and it's kind of like going away. Also, the book is going away from that old cable modem thing, because on the previous versions they talk a lot about cable modems, and I didn't agree too much with that. So the twin ax, yeah, is a two cables. That's why the coaxial is one single cable. The twin is twin axial cable, two cables. That's what's called twin, because it's two cables inside, and that it kind of works on the half duplex thing, so one transmit and one receive and things like that, and that way you can actually get more throughput through that same coaxial cable. It's made out of 26 to 28 gauge copper, which is easier to handle, and it can take rough handling, but it some of these cables, it depends on the type of cable, can be used for short distances, 5 to 7 meters, and another one's up to, it depends on the components, up to 10 meters. Some of the 10 gig connections are now done through twin-X cables, and with the twin-X cables, you can make a fairly good 10 gig connection between two pieces of equipment that are next to each other, and that avoids using optics with lasers and using fiber cable, a fiber patch cord that is expensive. So with using coaxial is more economical. There's an example on the next slide. So this is more like what the coaxial cable would look like, and that would have a small interface, the same interface that the optical modules would have. So they give you the same performance of an optical cable, but like I said, it can give you 10 gig, 40 gigs, or 100 gigs. So now we're going into the 25 gigs. When we get into the fiber, we'll talk a little bit more about that. Now the twisted pair cable is usually 0.4, 0.8 millimeter diameter, right? Those are two wires twisted together. That's why it's called twisted pair. Each pair of cables are twisted together. Normally you have 4 pairs of wires in there for a total of 8 wires. Fast Ethernet will use 2 pairs, one for send and one to receive data, whereas gigabit, it will use all four pairs to send information, to send and receive. Now, something interesting on gigabit is that you need all 4 pairs to get across from one end to the other end, no miscommunication or no errors on the punching the cables or making the connection, because if you lose one of those 4 pairs, the connection drops down to 100 megs to fast Ethernet. So if you're testing a cable or you connect something and it's supposed to be gig supported on the computer side and gig on the switch side, and you cannot get a connection faster than 100 megs, actually the computer will try to sync up. They will try to communicate at 1 gig, and they will drop to 100 megs. If they cannot communicate 100 megs, they will drop down to 10 megs. So if they cannot sync up at 1 gig and they drop down to 100, chances are, I'll say 99% of the time, is that you're missing one of those pairs because you need all 4 pairs in order to do gigabit. Now, a twisted cable, you get your Cat3, which used to be used for voice cables for the old analog or digital phones. And you got Cat5, Cat5e, 6A. 6 will support 10 gigs, 7, 7A, and 10. For networks, you want 5E, which is E enhanced. The cable would actually say 5E or 5 enhanced. Cat5 is not recommended for gig connections, only for 10 or 100 for fast Ethernet. Remember, fast Ethernet is 100. Ethernet is 10. Fast Ethernet is 100. Gigabit Ethernet is 1 gig. But the category 5 transmit well on 10 or 100, but it will not. It will sustain 1 gig, but you're asking for trouble. You'll get some errors at some point. So honestly, any cable that I get a hold of that is a Cat5, I just cut the ends and throw it away. I don't want to use it. I don't want to keep it in my house. I don't want to keep it in my office. I don't want to keep it on my box of cables, because if I grab it by mistake, something quick, and I just connect something with a Cat5, everything else now is like 1 gig, unless it's an alarm system or something like that they want to save money and they're buying Cat5 cables, maybe. But make sure that it's a separate color, so at least you know that at least all your Cat5s is the shield is it's a specific color, so you know which ones are they. And as we mentioned before in the previous chapters, there are 2 types of cable: the shielded twisted pair and the unshielded twisted pair. Shielded twisted pair, of course, has a shield around it to protect the cable or the pairs inside from EMI, any other static signals and disturbing the communication. So the STP will have a shield. That shield is a foil or a braid, either way, that will prevent those electromagnetic forces coming in there. Sometimes that shield is grounded to protect the equipment, and you will see, because the jack, the RJ45 jack, will have like a metal shield on it to make sure that foil, it's connected to ground. Okay, so yeah, it has low noise, and it depends also the thickness and the grounding mechanism and the symmetry of the shielding. But It's just to protect you against that. Newer type of cables like the Cat A, the wires are more twisted together. I think I mentioned that before, that the category or the cable actually means how many twists you have per inch on the length of the wire. So Cat 8 will have 8 twists. All the pair cables will be twisted 8 times within 1 inch. If it's a Cat 6, you'll have 6. 6A is just an enhanced Cat 6, and that's a better cabling, but it still have the 6 twists, right? But it will give you a very good high bandwidth, something that you can get, like you get on a fiber optic. But usually this for high speed cables, you use only short distances. You cannot use that for long distances. And I like this example. This example shows you the four cables, um, the brown, brown, white, orange, orange, white, green, green, white, green, white, and the blue, blue, white. Those are the four pairs that you have. Sometimes they can be like on this one separated for better, shielding of the cables. And then this is nice because it shows you both that you can have a foil and also the braid. So it's a braided copper. So those two combined will protect that inner cables inside those four pairs against any interference from electromagnetic interference. And this is a Cat 8. If you see category 8, you'll see that every pair has a shield independently from the main shield. So you got the braid, the shield, and then each pair has its own shield together, and that's just to minimize the noise in that wire. So that prevents also the crosstalk between one pair of wires to the other pair of wires. That just it completely enhances everything. That's why it's a category 8. And the UTP is just with no shield, same cable, same pair, same type of copper, same thickness, same everything. It doesn't have the shield. It is more economical, of course, because it doesn't have that shield, but and it's less resistant to the noise than the STP. Nowadays, the prices have changed so much that sometimes you can actually buy the STP almost at the same price of the UTP because the prices have dropped so much. That or you might just spend just a little more and get STP. So when you run those long cables, 90 meters or 80 meter, it runs the cables that's super long, or if through the whole floor, that horizontal wiring, remember the horizontal wiring. So when you run that cable in, you might want to run STP just to prevent any interference on the cable and make it more efficient, much better communication, and a more robust communication. And if the price a point is not too much, then why not, right? So when you compare the two, they're very similar. The throughput is the same. It's not going to change. Cost will vary, right? STP will be a little bit more expensive than UTP. Connectors are the same. You use RJ45. So when you see a jack on the wall, you're not going to know if that cabling behind the wall is STP or UTP. You don't. There's no way to know. The difference is the noise. That STP it will be protected against the noise. The length will be exactly the same, 100 meters. It's not going to improve anything. It's still going to be limited to 100 meters, right? And you will get communication from 1 meg to 10 gigs. 10 gigs, of course, if that UTP or STP cable, it's a category 6, category 7, or something like that, or category 8 will be more for like short distances. But for 10 100 meters, category 6 will work there. But for short distances, yeah, you can get good throughput, better communication, better performance. But for like higher categories, then it will be for short distance. Remember that you're twisting that cable inside, so every twist, it kind of shortens, takes that a length of the cable and shortens that. So that's why for category 8, they recommend only for short distances. But 6 and 7, you can still run category 7. I know 6 for sure. 7, I doubt a little bit that can get to 100 meters. But now to the desktop, we're not there yet to run 10 gigs to a desktop connection to the back of your computer. We have it at the downtown at the Magic Center. We have some computers that they run at 10 gig to the switch to the workstation, but it's within one lab, so the connections are probably within 50 meters. They don't go that far, but we have it. Now, to wire the connections from the patch panel to the wall or on a patch cord from end to end, you have to follow two standards, either the TIA EIA 568A or 568B. They're both very similar. It's just one pair of the cables that is switched. But as long as you switch on both ends, then the cables are exactly the same. There's no difference between the two. The jacks look the same and it's everything the same. Most likely, if you have any problems, it's because things are not terminated correctly. Either when you terminate the cables on the back of a patch panel, when you punch it down, or when you crimp the cable for the RJ45 jack for the wall. Sometimes a cable might not just connect very well on it, and then that's when you'll see that you're missing one pair. But that's why when you run cabling, you want to leave some slack. So with that slack, you can always cut the cable a couple inches and then re-terminate the cable again. That's where that slack is so important to have there. Yeah, you cut 1 inch and something like that, re-terminate and test it again to see, make sure that it goes the same. And this is something that I always used to get confused. But if you look at this drawing, you see the little tab that is drawn on the two light blue connectors, right? That means that the tab is on the other side. You're not looking at the connector from the basically from the bottom, which is the side with the tab. If you flip it around where there's no tab, then you can count the cables from 1 through 8. If you see on both of them, 7 and 8 has the brown pair. That doesn't change. The blue pair goes always in the middle, and if you notice, the order is flipped. You got white, blue, and then the blue cable. If you look at the brown, you got brown and then brown white. But on the blue is blue white and then the blue. And then the difference between 568A and 568B is the position of the green and the orange pair. On 568A, green is on the first position, pair 1 and 2, and orange goes split into 3 and 6 because you got the blue in the middle. On 568B, orange goes first, and then green is the one that gets split between 3 and 6. It follows the same order that from top to bottom, you got solid and then stripe. And then for the orange, you get solid and then stripe. And remember, blue is backwards. It's stripes and then solid. These are the standards for the TIA EIA. So when you do a job, it needs to follow these standards. There is a protocol. You need to follow that, right? If you look at the figure 517, that is the connection for a fast Ethernet 10100. On the actually fourth column, the fast Ethernet, you see transmit is on pair 1 and 2, and then 3 and 6 is the receive pair. Whereas on the gigabit, which is the last column to the right, each pair has bidirectional, plus and minus, bidirectional, plus bidirectional. All of them are bidirectional. So you communicate through all 4 pairs, and that's the one that if you miss one of those, it will fall back to the fast Ethernet function, which is the first and the second pair, which is 1 and 2 and 3 and 6. And the 4, 5, and 7 and 8 and basically unused unless you have PoE, power over Ethernet, where power Ethernet is injected on those pairs for fast Ethernet. Gigabit is special. Gigabit, it has a signal and power over every single pair. And that will give you more power because now you got 4 pairs that can transmit the power comparing to fast Ethernet that you have only 2 pairs that can transmit power to power devices. We'll get into that in a little bit. So what we call a straight through cable, it's a cable that is terminated at both ends identical. If you look at one side and you see the order of the colors, and you look at the other side, you see the order of the colors, they're identical. That is a straight through cable, meaning that the pair that goes on 1 and 2 on one end, if it happens to be orange, then it's orange on the other end. The last pair is brown. So if you have brown on the last pair, 7 and 8, on the other end, you'll have 7 and 8. Now, if you do a rollover, completely flip it around, right? Flip it around, the 1 through 8 is now 8 through 1. Flip on the other side, and the colors match like that. That's what's called, it's like a mirror image. That's what's called a rollover cable. Some of the console cables use that. Here says also called console cable, but not all the console cables are like that. Cisco started to set up like some kind of standard. A lot of companies follow that, but it's still not 100%. You still get some equipment that might be 5, 10 years old that it doesn't use straight rollover cables to connect, to connect for a console cable. And here is the power over Ethernet. So PoE is an IEEE standard 802.3. It depends how much power you have on the wire. That's the type it will be. If you have AF, is the old regular PoE, and that provides 15.4 watts. That's the standard. A lot of the access points, to some of the new wireless access points, require more power. So you can have what is called the PoE Plus, that it delivers 25.5 watts, and that's the standard is 802.3AT, as in Thomas. Now, the way I remember that is that when I see AF, that F to me, it stands for 15, so it's 15.4. And to the AT, I think of T as 20, so it's 25.5. I still have to remember the numbers, but it helps me remember that the AF is the 15.4 and AT is for 25.5. So easy way to, a mind trick to remember that. Sometimes I say like, yeah, the one is like 20 something watts. So people know what I'm talking about. So when I don't remember exactly 25.5. But that's how you distinguish them. But so a lot of the new equipments kind of deliver PoE. They're even PoE plus or they're PoE plus plus with more power. And we're getting more things. Nowadays, actually, some of these switches provide enhanced PoE plus. And what they're doing is that you can power up the lights in your office, LED lights from the switches, which is pretty cool. So you put now you're throw more cabling in your area that will provide power, not Ethernet, there's no network communication, but just they take advantage of that piece of equipment to provide power into it. Now, the smart way that they did is that you can reboot the switch without interrupting PoE. So you have to reboot your switch for whatever reason. The switch can power down the network portion, but not the power portion. So your lights will still be on. A lot of those fob readers on the wall that you have to open a door or something like that, they're fed with a power over Ethernet cable that provides network connection and also provides power to power up that device on the wall. So PoE is going everywhere. So you power all kind of power devices. PoE requires Cat5 or better. Hopefully you're not going to have Cat5 on any office, any environment at this moment. Everything should be Cat5 or better. And PoE, what it will do, it will connect to a device and they do some kind of negotiation to see how much power the device needs, and they will deliver that. Depends if it's PoE or PoE plus, right? If you don't have a switch that has PoE built into the switch, then you can have a what's called a PoE adapter or PoE injector. That what it is a small device with in and out connections. So you connect your Ethernet coming in, and then on the way going out, it will provide PoE plus the power. It will inject the power into the Ethernet. So now you got PoE. Sometimes it works. If I have a small deployment of access points, I have only 4 access points in an area, well, am I going to buy a 48-port PoE switch, full PoE on 48 ports, when I don't have any other devices that are PoE, no phones, no anything like that I require, only it's those 4 access points. So at that point, I'll buy 4 injectors, plug in those 4 injectors, and I feed my access points like that. I don't think there's a need sometimes to buy a full PoE switch. Or now you can have some that are partial. The half the switch is PoE and the other half is not PoE. So you can leverage that and get a little discount, because PoE switches are expensive. And the more power you require, they get more expensive. So here at the top you have a PoE switch, right? You got your power strip providing power to the switch. Your LAN provides the data, and over the same wire you provide power and data. Very good for cameras because you'll power the camera and also Ethernet to the camera. On the bottom half you have a switch that is non-PoE switch, so you can have power going to an injector. So you take data into it. And when you get out on the second port, it's power and data combined. And if the device at the end is a straight PoE, it is a PoE, like the camera on top, you can just plug it in directly and you'll get, it'll receive the power. If it's not it's a non-PoE security camera or no non-PoE device, then you can get that splitter back. So it splits the data into the power, and then you connect the power to the camera and the data to your data connection. And that's how you take the power to the device. So some of the standard you will see on Ethernet, which is again is your layer one, right? This is your we're talking about everything that we talked about today is this video is all layer one. Um, is able to communicate at Ethernet, fast Ethernet, and gigabit. So the device will do a negotiation to see how fast they can go, and they will start with the fastest. They will see they can go 1 gig. If they cannot sync up at 1 gig, they will drop to 100 megs, which is fast Ethernet. And if you cannot do that, it will do 10 megs. If it needs to, it doesn't show here, but yeah, you can have 10 megs. The Ethernet you can get, yeah, you can get 100 gigs on cable. I haven't seen one yet. I've seen 100 gig on fiber, fiber optics, but not on a cable. On cable, the fastest that I've seen so far is 25 gigs. I've seen 10 and 25 gigs. But the new standard, it's coming up. It's a lot of devices already support and switches support 2.5 gigs on the same cable. So you have fast Ethernet and you got 2.5 gigabits. 1 gigabit or 2.5 gigabits. And the 5 gigabit I haven't seen yet. That I haven't seen switches like that. There used to be a standard for 40 gigs, but 40 gigs is going away. 40 gig was actually a 10 gig that they put 4 together to get the 40 gigs, but that's kind of like going away. But the new standard, it uses 2.5 gigs. A lot of access points are using 2.5. On a desktop, yeah, 1 gig, I think so far at this point in technology is sufficient after today, 2022. But eventually, I guess more demand, more communication, more things might require 2.5 gigs or even 5 gigs. But it's a way to provide some leverage to go up to the 10 gigs. If you notice, the 2.5 is doubled to 5, and the 5 is doubled to 10 gigs, right? If you get a 2.5 and do a 10-fold, then you get 25 gigs. So those are the numbers that actually go into. I think the 40 gig is already on its way out. So the next layer one medium is fiber optics, right? Fiber is made out of glass, but it's more like a silica. It's a plastic fiber. It's a silica that is somewhere close to glass, so that's where it's a little flexible. It has some flexibility. You can have some bend radius that allows you to do some bend on the fiber, right? Rather than sending signals like the ones and zeros and electrical pulses, this is just a light. Is it light or no light, right? A link between two buildings or two sites or two areas with a fiber with no equipment in the middle is called a dark fiber. That's what it's called, a dark, because there's nothing on it. There's no equipment in the middle, and then you shine the light on both ends to communicate. All of this, they use LEDs, which is the light emitting diodes, or lasers that will send the signal. Most likely will be a laser for faster speeds. Some people tend to look at those things right at it. It's a little red glow that you'll see on those lasers. Please stay away from that. There's a warning on those things that it might cause damage to your eyes, so don't look at it. I've seen engineers actually looking at it, goes, oh, yo, look, there's a light, there's a signal. Please don't. There's equipment that is made for that you can put there and receive and see if you're actually seeing a light or no light. That use that piece of equipment. Don't use your eyes, because it is a laser. Even those laser pointers, if you look at those, which are low power lasers that are used for presentations and things like that, it has a warning that says do not look straight at this, because it might cause damage to your eye. If that's a laser pointer, imagine what this laser is made to communicate at 10 gigs or 1 gig. I mean, and this 1 gig and 10 gig we're talking about, that's a frequency. That's how fast the laser goes on and off. It could make some damage. So anyway, fibers, um, is glass or plastic. It has a cladding which goes around that, and then it helps to reflect the light back into it. Remember, the light nature of the light is to go straight, right? And when you bend the light, when you bend that fiber, you're actually bending that light, and light doesn't like that. So light wants to go straight, so it will bounce back. It will do like a reflection inside when you bend that fiber. So that's why you're trying to keep your fiber on a straight lines, and then do a bend, and then go another straight line, and not to bend too much, because every time you bend, you lose. There's some reflection, and you lose, and some light would escape. Then they have an outside cladding that is, a plastic buffer to protect the internal cladding and the core. Some of that is also covered with Kevlar. Kevlar is the material used on bulletproof vests. So it's Kevlar is on those strands in there to provide more protection to the cable. I say cable, I mean fiber. I meant fiber. The protection to the fiber. But this is a typical fiber. You see that it has the fiber strands at the end, and then it has the cladding, the protection with different colors. Then there's another protection around it. It's like an orange. You barely see it at the end, like in the middle. And then this fiber cloth feather-like, it's the Kevlar that allows to protect the fiber a little more, and then your outside um, shield or coverage that it will make it waterproof and stuff like that. Now, with the nice thing about fiber is that you can run fiber underwater and it will not damage it. Cable, on the other hand, it will start corroding. Water goes in there, starts corroding, and start like arcing one with each other. But with fiber, nothing would affect it. It will go through mud, through water, anything. You can put it on the water, and as long as that plastic doesn't decay, it will be there forever. A lot of the country to countries connections under the ocean, they're just basically laid down on the ocean. It's not that divers will go in and clamp it down and put some support. No, they just kind of like take a ship and they go in a straight line, and they start throwing the cable, and it just gets laid down. Of course, it is marked, so all the ships that go across and stuff like that doesn't damage the fiber in case that they need to touch the bottom. It happens a lot on harbors that if there is fiber there, some ships will actually drag their anchor and might catch one of these the cable fiber cables, and when they lift it up, they rip the cables. They're usually marked, and they should have charts where it says where the cables are, so they don't throw an anchor on top of it and yank it out. But those accidents do happen. But it just like that, it's just laid down. Like I said, there's no divers that clamp it down and put supports on the water. Nothing like that. It's just kind of lay the wire. It's so well protected, it can be underwater for years, years and years, and nothing will happen to it. So what are the advantages of the fiber? Well, it's high throughput. Now you're going at the speed of light. Although on a copper cable, you send electrical signals, right? Electrical signals are electrons are flying through. Electrons travel at the speed of light, the same speed. It's just that light, it has through fiber, it has there's no attenuation of the signal. You lose some light, but not as much electrical signal when you go on a copper wire. The copper wire has more attenuation of the cable. We talked about that term before. Attenuation, when you lose signal. A wire will have more attenuation than a fiber. Fiber, you still have some attenuation, like I said, because when you bend, some of the light tries to escape. So when that light escapes, it's lost. And if you bend too much, it's like you can lose so much light that it might get to a point that you don't get enough light for the receiver to interpret that. It's very high noise resistant, right? There's no way to have electromagnetic forces affecting this fiber as long as they're protected and covered. There's not going to have any interference at all. That provides security because now you cannot tap into it. If you tap into a wire, the electrical devices that can actually sense the pulses of electricity going through the wire, and that's they can put a tap and just listen to that communication. On fiber, you can't have that. There's no way to clamp something around the fiber and capture any light going through. You know, um, and then the distance. We have some of the optics here at the college that can go easily 80 kilometers, and they can some others can go further. It depends on the intensity of the laser. The stronger the laser, the further you can go. We'll talk about that later. But there are multiple types of lasers. But you can have a laser, and the price is not much different anyway. But you can get one of those lasers, one of the modules that has a higher laser with a different wavelength. So that wavelength is able to go further away because it is a more brighter laser than the others. So you can go, like I said, for the distances. We have a fiber that goes from, I think it's from the medical campus to the north campus. It's a dark fiber, and there's no equipment in the middle. And we connect one piece of equipment on one end, the other one the other end, and it connects fine. We used to have one from Kendall to Wilson campus, and also we just had those 80-kilometer optics, and it will go through it. Right now, the drawbacks is expensive because it's a lot more expensive than the twisted pair. The modules themselves, the lasers themselves, are very expensive. If you buy the name brands, we're talking about $2,000 each, so it's $4,000 per pair. You need one on each end. If you buy some of the more aftermarket and so quality, you can get them for like $500-800 each. So it's expensive, but hey, you can communicate 10 gigs over long distance with no problems. To install fiber, you require special equipment. Some of that equipment is really, really expensive. One time I was trying to do that for my kids at school, and they had a fiber that it was damaged, and they wanted to like redo the ends, the connectors. And I looked into it, and the terminators, the actual connectors were expensive, and the tools we're looking at like over $1,000. It was just to terminate like about eight fibers or something like that. And so it was not worth it. It was not worth it. If I do that as a contractor, and I do it very often, yeah, I can buy equipment that is $5,000. And if I use it enough, then of course that it will pay back, because when I charge for that, my return is pretty quick, but it is expensive. Now, the different type of fibers. One of them is single mode fiber. The light traverses the fiber in what's called modes. So single mode fiber is it's just one mode. Mode is basically the way they transmit into it. But the single mode has a narrow core. The core is very, very small. It's 8 to 10 microns in diameter. When I talk 8 to 10 microns, it's like the size of a hair, a human hair. That thin is that fiber. Um, so the laser goes through it, and the reflection is very little. That's why it's called single mode, because it tries to traverse through the middle of that core. The laser shoot right in the middle. It doesn't disperse. It tries to traverse on one, right? It can go for miles without being repeated, right? And a single mode can be used for short distances, but it's usually used for long distances. For short distance, we have the multi-mode is coming up next. But everything that runs on the internet backbones are usually single mode fiber. At the college, everything that we have from building to building is single mode fiber. We used to have multi-mode, probably I would say like 10 years ago, and in the past uh, 5 to 7 years ago, we replaced everything from multi-mode to single mode. Like I said, it's more efficient, and we wanted also to go to 10 gigs. So the old fiber that we had, the multi-mode, it could carry the 10 gig, but it was not going to be like good communication. So it was going to be like kind of like borderline performance. So we decided to just redo all the fiber, and we installed single mode fiber across the college. Now, the multi-mode fiber is a thicker core, it's a larger core. Single mode fiber is 8 to 10 microns. This is 50 to 62 microns. This is a much thicker. I mean, as you can see, 8 to 10 to 50 to 62. And it just a thicker fiber is older, is a older technology. The same, it uses the same method as the single mode, with LED or a laser. Um, it gets more attenuation than single mode. What happens with multi-mode is that the signal, the light, is shot on the fiber in an angle, not straight at the middle, but it's actually more into an angle. So what happens, it will hit that wall, the cladding, and it will bounce back inside, but it will bounce back at an angle, right? The loss of reflection. So it will reflect back at the same angle that came in. So when it comes out, it goes at an angle and it will traverse the fiber across, hit the wall again, and come back and zigzag all the way across. So by that zigzagging, it puts more latency, and then the signal degrades more because every time it bounces back, some signal tries to escape. So that's why multimode is used for short distances, and it's not as efficient, than the single mode. Right, so for short distances, you can connect router switches together, servers, or anything that is close by. The lasers are a little bit cheaper. The fiber is a little bit cheaper. So for something that you do within your data center or within your MDF, to connect the things together like locally there in the same room, single mode, I mean multi-mode, it would just be sufficient, right? Most of the time you go into a finer a fiber panel where you have single mode and multi-mode, right? That you can do a distribution panel there to see what connections are single mode, what connections are multi-mode, so you can have a panel like that. Now the connectors are similar to each other. Hello, 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 hello. Now, on the fiber connectors, don't be deceived. Fiber connectors can be the same for single mode and multi-mode. There's no such a thing as a multi-mode connector, single mode connector. They could be the same. The only difference is how they accommodate that core, if it's the single mode or the multi-mode core. And the tip, which is called the ferrule. The ferrule is a little tip that extends where the fiber goes in, and that will be different sizes. Of course, for the multi-mode, it will be thicker than the single mode. They come in the way that is finished. So it's ultra polished connector or angle polished connector. The angle just that is cut like in an angle. That depends on the manufacturer, how the patch panel is made, how the devices are made. In the old days, every time you terminate a fiber, you put a connector, it had to be like polished by hand, and there was like equipment to do that. There were like a microscope that you can actually shoot a light and then look at that termination there to make sure that it was polished correctly. Nowadays, those things are done so well that at the end it has like a gel, and it already has a finish end. So the fiber all has to do is like get and get all the way to the end and make a contact with that the end lens or glass at the end, and then it will make that connection to transmit the light. But nowadays, like I said, it was so delicate that if you drop a fiber or drag it on the floor, it will like damage the that polished end, and it had to be redone again. But like I said, nowadays it doesn't happen like that. You still have to be careful, right? But it's not as critical. The ferrule for the single mode fiber, the different types, they're very small one. The 1.25 millimeters connectors is called the LC. For the 2.5 is a little bigger, thicker. That's is for the SE connectors, the standard connector, or the ST, which is a straight tip. There used to be the MTRJ, the mechanical transfer razor jack. That was a pair connectors. It was very small. I used it when we had the ATM technologies, the asynchronous transfer mode, that it was in the book, but it was taken out. But asynchronous transfer mode was a way different from Ethernet to communicate between two pieces of equipment. And at some point, they were using MTRJ connectors, but those haven't seen them in, I would say, like about 15 years or something like that, that I haven't seen any more equipment with MTRJs. But I'll bring to class some of those connectors. There's also some reference on the videos on Blackboard that you can refer to, some of the pages that I pointed to, that it will show some of the different connectors that you can have. Now, everything can connect to everything. That's where you have media converters. Media converters will do anything to anything. You can convert multi-mode to single mode. You can actually convert copper. If you have a copper cable that needs to go to a fiber, you can do copper to fiber conversion and then get that connection to go to fiber. You know, from copper to go to fiber. We have that into one of the connections that we have, the Napa de Americas, that they gave us a 10 gig connection fiber, and my router only had a copper 1 gig, completely two different things. So I put that into a converter. The converter actually converts the 10 gig to 1 gig, and it converts also the fiber to copper. So rather than giving me 1 gig fiber, it gives me 1 gig copper, and I connect that to my router, and I get that. Now, what's interesting is that from that connection, we're actually paying for only 1 gig throughput. Remember, we talk about bandwidth and throughput. So the bandwidth that we have in that connection is 10 gigs. So it's a way big bandwidth of 10 gigs, but the throughput that I'm getting is only 1 gig. So it's a huge big pipe, but it's a very little, 1/10 of that is what I can consume out of that connection. So that I can convert that into my copper. That copper supports only 1 gig, and yeah, the 1 gig will be now full, the full 1 gig. But I'm not going to do more than 1 gig. I'm not allowed to do more than 1 gig. So that media converter works for me at the time, at that moment there. And we still have it connected. But you can do anything to it. Even though this slide shows you multi-mode to single mode, you can do multi-mode to copper, single mode to copper, or any combination that you need to do. Now, every time I mention the fiber modules, this is what the book talks about. They call it fiber transceivers. It transceivers because they transmit and receive. They're called fiber transceivers. They transmitter and receivers at the same time, and those are the ones that plug into the equipment. And they're called for the 1 gig. They will call GBIC. Well, it's spelled GBIC, GBIC. That was the old standard for Ethernet, the gigabit connections. Nowadays, with the term GBIC is obsolete because GBIC was a very wide connector. So now there's other type of connectors for the SFP. You got SFP plus. SFP is for small form factor pluggable, and you got this a small form factor pluggable plus, that the plus just supports multiple speeds, and the XFP is for the 10 gig a small form factor, and you got the QSFP, which is a quad a small form factor. Basically, it's combining 4 into 1, and you got the quad plus. And the Centum form factor pluggable I haven't seen yet, at least not at Miami-Dade, not at our college. But the quad SFP was the one that it will take the 4 10 gigs that combine into a 140 gig connection. It was very popular. We have a few connections like that. But like I mentioned before, the 40 gig is already on its way out. The new standard is if you're going higher than 10 gigs, you'll have to go to 25 gigs. And on 25 gigs, when you do a quad, you'll go to 100 gigs. That's the next step up. Now on this slide, please pay much attention that this must be paired, right? You cannot have a green transmitter on one end and put a blue receiver, a blue transceiver on one end and a green transceiver on the other end, because both are going to be sending, let's say one is going to be sending blue signal and expecting blue back, and the other one is only sending blue in green and trying to receive green. So they're not going to be able to talk to each other. So this is kind of like the frequency that you have on those. It's just that on fiber transceiver, it depends on the wavelength. So the wavelength, if you do the light, the visible light spectrum, when you go into higher wavelengths, you will see the 850 nanometers. That's the one used from multi-mode fiber, or the 1310 nanometers, 1310 nanometers. That's used for single mode fiber. So if you don't know also if a transceiver is for single mode or multi-mode, you can look at the transceiver itself, and you'll see that it says 850 or 1310. 850 is for multi-mode, which is kind of like a low frequency, right? Because it doesn't transmit that fast. And the single mode is 1310, 1310 nanometers uh, uh, wavelength. That's for the single mode. There are other higher 1450, and I can't remember any other at the moment, but the most common ones are those two: a 50 nanometers for multi-mode and 1310 nanometers, 1310 nanometers for single mode fiber, and they need to match. There's no way that you can have a 50 on one end and a 1310 on the other end, because they're not going to talk to each other. It's like two different frequencies. It's kind of like your TV sending you channel 10 and you're tuned on channel 4. You're like, I'm not getting anything. Well, of course you're not. You need to be on channel 10. So they need to match. If they don't match, you will not be able to communicate. So here it is. So for the 100 base SX, SX is um, for the fast Ethernet that uses the 850 nanometers. That's usually the wavelength for multi-mode fiber. And then you can have 100 base FX. There's also for fast Ethernet is a longer wavelength and is rated at 2 kilometers. Then you have the 1000 base SX, which is 1 gig, right? That uses the 850 nanometers. And the 1000 base LX, that is for longer distances. The one that uses the 13. It says here 1300, but it should be 1310 nanometers. The way it's actually supposed to be read, the SX is for short haul and the LX is for long haul. Long haul. So the long haul for longer distances uses a higher wavelength. And now for the 10 gig SR is the same thing for short reach, your short range, a 10 gig, and the LR for long reach, also at 1310 nanometers. Like I said, the SRs and the SX is 850, and the book must be wrong here, because I know that the LX is also 1310 and the LR is 1310. It's the same light, but one is for for the LX and the LR, but a different speed. So you cannot combine, even though they're the same wavelength. The 1000 base LX and the 10 gig LR is the same 1310 nanometer light, but the speed is different. So one is going to be talking super fast at 10 gigs, and the other one is going to like slowly receiving at 1000 base, and it's not going to understand. And when it's sending information back to the 10 gig at such a low speed, the 10 gigs a 10 gig base is going to say, what is that so slow? I cannot sync up with you. The frequency that you're using is different. One is using a frequency for 1000, the other one a frequency for 10,000, which is 10 times higher, and they're not going to talk to each other, even though they like. So everything needs to match. If they don't match, again, you're not going to be able to communicate. Now, the common problems, I already mentioned that. The fiber mismatch. You cannot have single mode and multi-mode connected together. Then it's just not going to work. The cores are made to transmit the light in a different way, either single mode or multi-mode. So you cannot connect a single mode to a multi-mode and expect the signal to go through. You cannot have SR for short haul connector and use it with a single mode fiber, because it is not made for that. The short haul uses multi-mode, and if you put a single mode fiber, it just doesn't match. They have to use the right fiber with the right cores, with the right modules at the right wavelength. If you don't match all those things, it's not going to communicate. So like I mentioned the wavelength before, yeah, it has to be exactly the same on both ends. That happened to me many times because we have the long reach, what's called the I didn't mention here, but the ERs. You know how we mentioned the SR and LR for 10 gig. Well, we have the ERs, which is for the 10 gig fiber, extremely. It's like 80 kilometer distance, and the wavelength is different. So one time we had a problem. We called AT&T, and AT&T went to test it. And he goes, "I don't see your light." And I told him, I said, "My light is not at 1310. My light is at 1450. So if you don't put a receiver for 1450, you're not going to see my light." That's because he was putting a piece of equipment, trying to read, thinking that I was using LR optics, and they were not LR, they were actually ERs, that uses a different wavelength. So that's why he couldn't see it. Dirty connector is very common. When it comes to time, there's always a gap, like air gap between the connections on either end of the fiber at the patch panel or the piece of equipment. So with time, little particles of dust can get in there, and it will cause problems. It's not like something that you need to clean every month or every other month. It's something that might happen, like, it depends how dirty the place is, but it could happen every I don't know, 2, 3, 4 years, and you might want to go there and use compressed air and kind of clean them up. There are also some wipes that you can use, like an alcohol wipe, especially made for fiber, not just any regular wipe, because it has to be lint free, so you don't leave any lint on it. So you clean those connections. And then lost link is something happens, either a one of these lasers fail or something breaks the fiber in the middle. It happens along the way. There's so many connections or multiplexes or patches or splices that it might go bad. God forbid it happens here in Miami that there's an accident and the fiber is going aerial through the a light poles, and when they hit a light pole and they knock down the light pole, you lose that connection. So the company providing that fiber needs to reroute in a different way, reconnect things and patch in a different way. But it happens. A lot of digging sometimes here downtown. It happened many times that they always digging on the streets downtown. And if the companies are not careful, they will dig in and actually pull fibers, and they have done it quite a few times. So that's how you lose the fiber. For troubleshooting a cable connection, the easiest thing is to look at your lights on your equipment and your computer. If you have a link, you will see on the back of your computer a link light, like a green light coming on. Most likely is a steady light. If there's activity in the line, you'll see that light blinking. That means that there's some communication going there. If you see some red or amber light, it might indicate a problem. With the amber, you have to be careful, because sometimes some of those network cards, the lights, if it's green, means they're connected at 1 gig. If it's amber, it might mean that is connected at a fast Ethernet, that it didn't link up at 1 gig, so it'll give you a number. The red, I haven't seen on some equipment, not on the network cards. And the network card is if it fails, it doesn't get a connection, you don't get a green light. It just goes completely off. So one of the first things you need to do is that you can also go to the switch and take a look at the switch, and you might see the lights there, and look at that. If you suspect that the cable is broken, then there are ways to test that. There are multiple testers that will describe that on the next slide. One of the old testers was a tone generator and the tone locator probe. It's a pair of devices that you use them together. One of them would actually generate a tone, and when you connect it on one end of the wire, it will send a signal through the wire. And then you got a probe that is more like a sensor with a tip on the sensor, that you start like touching the cables and see where the signal is. That is very useful when you have a bundle of cables and you got 50 cables in there, and you're trying to trace one cable that you don't know where it goes, or where the wire terminates, or when you want to identify those cables, to number them and put them, and document those cables. Then you can put a toner on one end, and then you go along the cable to see where the other end is, or which of the 50 cables spraying out, which of those 50 is. So you use that one to locate that cable. Once you locate that cable, you can use some kind of a network tester to put signal across and make sure that the signal goes across, and they test the pairs. There's some of them would actually go and test every single pair to make sure they all work, and those testers will definitely give you a good, a good a result and see on the testing. I'll bring one to class. I have one that in my office that I can bring into the class and show you. They're a little bit expensive. Some of them, some of the basic ones are cheap, $20, $30, $50. The most expensive ones with an LED display and graphical displays and stuff like that might go between $200, $300, $400. But it depends on what kind of work you do or how often you do it. If it's a large workplace, then it'll be very beneficial to have one of those testers on hand. Actually, some of them are so good, the $300, $400 ones, that if they're configured correctly on the switch, and when you put the tester on the cable, it will tell you what switch is connecting to, what VLAN you're connected on. If it gets an IP, so it will touch the HCP. It will test if you get DNS. It will try to go to google.com and see if it gets a DNS resolution. So those are really good testers, and it will test everything on one connection. I'll bring one of those to class. Now, I still don't know why they put multimeter on the book to test this. I mean, to test resistance, voltage, and impedance. Yes, a multimeter will do all of that. But for a network, no. I do have it just to see, sometimes to see if I got power. You can also see if you have a short circuit, but any of those cable testers will do that for you, and not use a multimeter. Multimeters are very awkward to use because it's just like a two-prong tester that you test one end, and you have to loop one end, the other end of the cable to see if you get it. They still have it in the book. I don't know why, but in my professional life, I don't use a multimeter to test anything related to networking. Like I said, the only thing will be to test if I get 120 volts on the outlet or something like that. But for that, you have other ways to test it too. So these are the ones that I was talking about, that, you got a cable tester that will do everything. It will test all the pairs. It will generate a signal. It will send that. It will try to receive it on the other end. It will give you a series of light or tone just to make sure that, pass or fail. Some of them will verify if it's UTP or STP. And if the pairs are going correctly. Some of them will actually tell you the length of the cable, so you can test it and from end to end, and it will tell you based on the trip time, how long the cable. Very, very, very close estimate if it's a 6 feet, 10 feet, 20 feet cable, something like that. That's how you can test a cable to make sure that you didn't go beyond the 100 meters. You can do that. They also have similar tests for fiber optics. Fiber optics will send like a light pulse to make sure that the light goes across, and you can see it on the other end. So they're very, really nice optical testers to test a fiber. You can also do what's called a loop that on one location you put the loop, so it loops the two fibers. Fiber is always a fiber pair, so it will send one back, and then when you go from one location, you send a signal through one, you're supposed to receive back on the other one, and they will do that. Or you can have a piece of equipment on one end and the tester on your end, and when you run that, it will test the quality of that fiber connection. So those are very useful to have. See, and these are the ones that are more sophisticated. They will do the attenuation, the near end crosstalk, the resistance of the cable, pass or fail. You can store the results, send them to a report. Especially if you're a contractor, you're doing cabling, it's very useful if you're capable of saving all this information and then do a printout for your client to say, hey, this is what it was done, or just to provide management and said, hey, we run all these cables, the cables are done, and these are the reports. So if someone comes after us and damages the cable, something like that, is not us. The cable was already done and tested, and they will do some of them graphical attenuation and all that. It's all kinds of different things, but some of them are, like I said, more sophisticated, more expensive testers, and they are there. We have maybe one or two through the college, whereas the little ones that like $300-400, each tech might have one each. Or some of the departments might have their own, so they can test connections before they call us. So they some of them are expensive, but for the quality of results that they give you, they are worth it. Now, if you go to the extreme, you can have a TDR, the time domain reflectometer, which is 1/4 copper or the optical one, and that will measure the distance between the node and the installation and the propagation of the signal, and how the performance of everything. The TDRs, those are quite expensive, but it will test everything. I say even those bends and attenuation over the cables and fibers, it will give you all that. But the TDRs or OTDRs are quite expensive, and like I said, that's more for like a provider a piece of equipment. AT&T, they definitely should have TDRs and OTDRs. because it has so many customers and there's so many connections that they have that they will require something like this to verify a connection. But for a small enterprise, even for the college, we used to have an old TDR for the cables. It was mostly to use for the voice, so we can guarantee that the voice communication between campus to campus was correct. But once we went to voice over IP, we don't really require that, but we don't use it. It's not anymore. Like I said, it's mostly for like providers, Comcast, AT&T, or any of those providers. Now the optical power meters, I love those. It's a way to measure the light that you're receiving over, over the equipment. We have a problem right now, actually, between that medical connection to from medical to the North Campus, that the power that we get is not enough, even though we have optics, they're really strong optics, it misses every once in a while. So we put up a power meter, and then yeah, it told us that the decibels that we have or losses is just way too low. Remember the decibels when losses is a minus number, so the minus number that we got is just past the threshold that is considered acceptable. And nowadays, some of the network equipment would actually have its own measurement of power. So the router themselves, if you run a command, it can tell you how much light is receiving, how many dBs of power is receiving on light. So you don't need to have an optical power meter because the device itself can do like a self-check. But if you don't have access to the equipment and all you need to do is to test that fiber, yeah, then get an optical power meter to see if there's some problems on the signal. You will need that, like even at the college, if you have to measure the quality of the signal for fiber optics from building to building, especially if you're going, let's say, from one building to another building, and that building goes, I don't know, 6, 7 floors, so the fiber still has to go rise up to the upper floors, and you want to measure all the way from end to end. So you want to be able to have a reading of that power and see if it gets there. And if it doesn't, then you have to increase, the type of laser that you use in something that is like I was called a hotter, which is like a stronger laser. So it gets to that further distance, and it can overcome all the attenuation and the losses across the path from one end to another. Okay, so this is the end of the chapter. So we cover a lot of the layer 1 technologies for cable, like twin ax, and fiber optics, the multiplexing, and all those topics there. There's a lot of resources, a few resources that I put on Blackboard, so go to those. If you really also want to look on your own, you can always do any on the internet, any search engine. Whatever you prefer, if you use Google or any other, and look for fiber optics, for the SFPs and different wavelengths and things like that, and you get, if you want to get more information beyond what's on the book. All right, thank you. Now we'll be ready for the next.